No more small talk. Okay. So, welcome to today's beginner lecture. Today we're gonna go over circular linked lists. But before that, I wanted to discuss one other problem. I don't know if I posted it on the leak code questions. It's an easy problem. It's to get the middle of a linked list. I just want to start with that. So we remember what a linked list is like. And I'm just gonna do things that, yeah. And we'll say this is all right. So I'm gonna come up with an algorithm to return the middle node, the node in the middle. Okay. So what could we do to get the middle node? Any ideas to get the middle node? Okay. Yeah.
Maybe some a simple idea so far.
Yeah.
Just
Like.
define how long the list is
Okay.
first.
So okay.
Divide by 2,
Right.
and then go over it again for that
Mhm.
amount.
Yeah.
For
So.
that amount.
So she said that what we could do, well, we cannot just access length of the list divided 2. We have to actually first get the length of the list, right? And what do we do to get the length of the list? Well, we just go through the list, right? So I'm gonna go with, I'll call it def, no, lowercase, middle of list, linked list. Right. So we start with getting the length. So I'm going to call it the size. It's 0 at first. So while head. So this is to check that it's not none, not null. So while head, well, actually, cur equals head, right? Good practice is to do cur equals head. So
You read it too?
it's too small? Wait, which part?
All of it.
All.
Yeah, for the rest, just write later.
Okay. So while, this is better. So while cur, you do okay. So we have a size variable, and at first it's 0. So each time we we're here, right? And then we see that cur is not null, then we increase it, right? So here's cur, and then we move cur up, right? And then we see that it's not null again, increase it, and so on. And then we get 1, 2, 3, 4, 5, 6. So 6. So we get 6, right? And the middle is going to be the halfway point. And I'm just going to arbitrarily say that it's going to be that node. It's an even size. I'm just going to say it's this. So mid equals over 2, which in this case is 3. So we get mid equals divided. We're trying to do integer division. So min equals size divided by 2. This gets the integer instead of the float value, because size could be 7. And if you divide it by 2, you get 3.5. And doing it like this it turns it into just 3. It gets the floating point numbers out of the way. Like, this is going to return an integer. Okay, so then we got our middle, and now he said it's just loop up to the middle. So I would say get an iterator I equals 0. I hope they can see that. So I would say 0 and 1. Okay, yeah, this works. Right? So I would say I equals 0. Here's cur. It's not null. Then we put cur here. It's not null. Here, I is less than middle, which is 3, so we can increase it. And I said that this was going to be the middle. So cur is not null, but I is not less than 3. So we stop. So cur is left at this, and I said that was the middle, so just return that. Right, return. Can they see this?
Yes.
Okay, yeah, all right. So get the middle of the list. You just get the size, divided by 2, that's the middle. And you just loop it again up to the middle. Okay? That makes sense? So could this be done a different way? A different way? Huh? Any ideas? I'll give you a hint. Do we need to calculate the size at all? Or even loop again?
Could we use a counter as you made those?
Well, I mean, could do that. Well, you don't need a counter. That's what I'm trying to say. You don't need a counter or to calculate a number at all. So any ideas, guys? Where you don't need to actually calculate a number? No, not you. Someone else. I know you know what to do. No numbers at all. So we don't need numbers to actually get the middle of the list. Well, what we could do, right? Instead of doing all of this, of actually doing I plus 1, size plus 1, we don't need size. All we need are 2 pointers. Slow. So we're going to have, it's like cur, but we're going to have 2, right? And those are going to loop over, hello. So both are going to loop through the linked list. Okay. All right. So we have 2 node pointers, right? One is the slow one, one is the fast one. So the slow one, we're going to check if it's not null. The fast, we're going to check if it's not null. And we're also going to check if the one, the next to the fast is also not null. And you'll see why now. So I'll move slow up. And then fast, I'll move it up twice as fast. Okay. Do you see what's happening? Describe what's happening here.
So, I mean, one's going to be ahead of the other one, and then it's going to reach the middle first.
Yeah. Well, one's going to reach the end first, but one, since this one is moving twice as fast as this one, see, what's the middle of the length? That's half of it. So if one's moving half as slow, if one reaches the end, the other one's going to be at the halfway point.
When fast reaches the end, slow is at the middle.
Yeah, exactly. So you don't need to actually get the size right and do 2 while loops. You just need one. And so let's actually do it. So I move slow here, and then fastest. There is no curve. Get rid of curve. And so slow is still a thing, fast is a thing. Here. Okay. And so the while loop checks if slow is still there, it checks if fast is still there, and that fastest next is still there. So in this case, we move fast, now fast is null. So that means this while loop stops. And I said before that this was going to be the middle, right? Because the length is 6, and this is 0, 1, 2, 3. So this is the middle, arbitrarily. I just chose it to be that way. So slow is at the middle, so we return slow. Right? Right, yeah.
More of a question for them. So why are we checking the fast dot next?
Because
Wait. Like more of a question for them.
you want me to answer it? No?
No, like for them, like so they can think about it too.
Okay, oh, you want me to, okay, so why are we checking fast dot next?
Well, because when it reaches the end, the other one's 2 spots behind, so it'll be in the middle.
A little bit more basic than that. It's in this line right here, actually. This line. Okay, so the reason why we're checking that fast dot next is not null. It's because we're going to invoke it. And then when we invoke it, we want to check a variable attribute of it. So yeah, it's an attribute in object-oriented. That is what it is. Okay, so if this is none or null, it's not going to have a next variable. It's not going to be there. This is going to give you an error when you compile it, or in this case, I guess, interpret it because it's Python. So that's why you need to check for this one, so you don't run into an error where this is null and null doesn't have a next attribute. So, yeah, so that makes sense now. So that's why we're checking for that. Okay. All right. So that's one way to get the middle. Well, this isn't Floyd yet. Floyd comes a little bit from now, and the camera followed me.
Yeah, because you use the hand gesture. No, I turned it off.
Oh, okay, you turn it off. You turn off the hand gesture, guys. That's what happened for those watching in the stream. Okay. Okay. So we went over linked lists now and before last lecture. Erase. So today we're going to discuss circular linked lists. Right? So what is a circularly or circular?
Circular.
Okay. What is a circular linked list? So we discussed a linked list where it's just a chain that goes in one direction. So what's circular?
So last node would point to the head.
Okay. So 2, 3, 4. It doesn't matter. So he said the last node will point to the head, and that's what makes it circular.
Would the first need to point to the last as well?
Well, I mean, the first will lead up. So this isn't necessarily what you need to make it circular. No, let me put one in here. Let me put one in the middle. Well, I mean. Okay, I put, this is the, not that. There is no last one, and there is no first one, but you could have a head just to, keep track of it. So this could be the head, but it also could be this one. The point is that you can go back to any node. It's circular, so you can always go back to where you started. You could have started here, here, here. You'll always find a way, if you keep moving forward, to go back to where you started. Also, it is possible for, put it here. Okay. Is this circular? Some of it. So part of it is cyclic. So you can get from here to here, and then there exists a cycle in there, right? There's a loop. So let's say I wanted to find a way to check if there was a loop. What would I need to do? Detect whether it's circular at all. A linked list.
You could do the fast and the slow.
Right, we could, yeah, so we can do that.
The fast reaches slow.
They catch.
That they
Yeah, that they meet up, they catch up. Well, I'll keep it like that. I'll keep this. So I'm gonna do def detect. They can read this, right?
Yeah. Now put it closer. It looks much better now.
Oh, okay. Oh, okay. Detect loop. So yeah, just do what we did before. So we have a slow and a fast. So this is a Boolean, right? We're detecting. So it's either there is a loop or there isn't a loop. And so we should do the same thing we did before. I'm going to get there in the bottom. Okay, and right here. So slow and fast next. So what do we need to do, right? So we did before. So we just slow and fast. Okay. And then what do we need to do after this?
Return.
Yeah,
Slow.
If
slow equals fast.
yeah.
Return slow equals fast.
Or return true, right? If slow equal fast. So that means slow has caught up, not really, more like fast caught up to slow when it went around the circle. It went around the cycle and now it caught up. Then return true. So if slow equals fast, return true. But let's say there wasn't a cycle at all, right? That means fast is going to become none, or fast.next is going to become none, right? So like just so there's no longer a cycle. This is not a circular linked list. It's just a normal linked list. Well, a singly linked list that goes in one direction. Right? At that point, fast is going to become none, or fast.next is going to become none. So it'll just escape it. right? If there is no cycle, this will escape. But if there is a cycle, this won't escape, and this is the break, the return statement in the if. So all right, let me actually put it back. And this does work. This works for any cycle, like any at all. And it's some math that goes into this, some theorem, some concept. So let's just actually work on it, right? So we'll do flow and fast, right? We'll do flow and fast. Move fast up. And slow moves up. Fast moves up. Goes here. And slow. Let me do it again. Well, I'll move slow up first by 1. I'll move slow up again. And then fast goes. All right. And now they meet. They're equal. Return true. It escapes the while loop and well, it returns for the function. So it escapes the function. So yeah, this works for all cycles, like all of them. This is a working solution. And it is also a solution that is not create a memory buffer that is linear to the size of the linked list. No, that means that it's constant memory, right? It's just 2 pointers. That's it. That's the auxiliary memory you're using in the stack, versus making a whole other list that's the size of the whole linked list, right? So no matter what the size of this, it's always going to be just 2 extra pointers and not just n extra pointers. Okay. So the runtime is what? This seems pretty linear, right? Yeah, it's O of n. And the memory is O of 1, it's constant. Okay? So that was one way of doing it. Now, what's another way we could have done it to solve this?
I have a question.
Yeah.
Is there any way to know if it's a partial loop or if it's like a complete loop?
Well, it's just the text loop. I mean,
Because it's only going to return true. So is there any way to figure out if the loop is like the whole thing?
what do you mean?
So like in that loop, I can't access the first node.
Yeah,
To the first.
because the first node is not in a loop.
Yeah.
It's not in a cycle. It's just dangling. But you can get into the cycle from here, but then once you're here, right, you're just stuck in this loop, and you never reach there. This works to detect the cycle, true or false. That's all the point of this problem. So this could be done another way that is it's faster, but you have to use auxiliary memory that is proportional to the size of the linked list, or about, right?
Keeping track of every node you see?
Yeah, exactly. So we would keep track of every node we see. By the way, what I just went over was Floyd's cycle detection algorithm, also known as the tortoise and the hare, right? Because the hare is faster than the tortoise, but they'll eventually meet up if there's a circle, you know. So it's another way of doing it. We could have a hash set. This is a hash set in Python, right? We could have cur equal to head while right. So this is another way of doing it, which it takes O of n extra memory, but it is faster in terms of runtime, because you don't have to revisit some nodes you've already seen while looping. This will just, so basically, so once cur goes back here, it'll just return true. That's what I'm saying. Versus having to go all the way here and go through extra other nodes. Okay, so what's happening here?
So how are you adding the nodes to the hash set?
You're right. You're right. He's right. I missed the part. I missed that part. Okay. Yeah, that would have been an infinite loop. That would have given you time limit exceeded. Thank you for catching me on not actually adding it. Yeah. Yeah. Okay. See, that actually was a test for you all. You know, that's what that was. Okay, that might have tripped you guys up a little bit because I didn't add. Okay, so what's happening here? So we have a set, a hash set, right? I'm gonna put it right here. Actually, some data structure. Well, that's bad. Okay, good. So we're in the set, right? Cur is here. Cur is head at first, right? And we're looping. So while if cur is in the set is empty, right? So this fails, does not return true. S add cur. So this is, we're not putting in the data value. We're putting in the actual node itself, right? Because we may have repeating values. But let's just say, for the sake of this, that there's no repeating values amongst nodes in the linked list. We're just supposing that that's true. So we add it, and then we move cur up. All right, we go again, cur and S. Well, there's no 2, so we add it, and then we move cur up. And so on. And then, well, the ones that haven't been added yet, we're just going to keep adding it, right? And then cur is going to come back over here, right? So now we check if it's in the set again. And we had 3, we're on 3. And look, we have 3. So that means we already visited this node. So at that point, we just return true. And that escapes the loop and gives you the value that you're returning for this function. There is a cycle. There is a loop. So one is using a hash set, which takes up O of n memory. And the other one is using 2 pointers, doing the fast and slow pointers, that one moves twice as fast as the other, which takes up constant memory, so O of 1 extra memory. So it's better on memory than this one. But this one is faster, generally. So any questions? Yeah.
Is there a special case that this can only work in?
There's a special case where only this works? You mean for cycle detection?
Yeah, like the values of the nodes are not unique.
What do you mean?
Like for here, like what if they could repeat the same numbers?
You mean like the same? Well, that's the point. I just did this. I'm trying to add them as nodes, not as actual numbers. Okay, that might create some confusion. These are.
No, okay, you're adding the object.
I'm adding the object of the node, not the actual value. So we're adding the actual node pointer, the node reference. That's what we're doing. We're doing nothing else but that. not the data value, of course, because they might repeat, and then you get that problem. Okay.
So in this hash set, you were like adding the objects.
Yeah, yeah. We're adding the. I think more specifically, they add the reference to it, right? Because the reference is it's like a hex or an integer.
Yeah, it's exactly that.
It's a hex number in memory somewhere in RAM, and you just has a value there where you might store the object. So we're adding the object, not the value inside the object. Okay? So that was the other way of doing it. Which one do you guys like more?
I had the tortoise and the rabbit one more.
You like the tortoise and the rabbit? Or hare? I think it's a hare. You like this one more, or just get the... You like the other one better? Yeah.
You said that this is faster?
Yeah,
Oh, yeah,
this is faster. Because the slow, which is where, that's where you do the test. It depends on slow, whether it catches up to fast, right? Because it might go over some other nodes it was already on again. Here, well, we're gonna suppose cur is slow, because if you think about it, cur is moving at the same speed as slow. It's just going over one, just like slow was before. And we're just checking if we've already visited that node. So we don't go over nodes that cur already visited, right? It only goes over that one time, and that's it. That's what makes this faster.
Big O, they're the same.
Yeah, but yeah.
In T,
Yeah. In terms of time complexity, they're the same, right? This doesn't become the slow and hare does not become quadratic or log linear, because of the process it goes through. It's still linear, right? It's still gonna be one loop. It's not gonna be a nested while loop or for loop or whatever. It's just one loop, right? And it will end, right? Like slow will catch up to fast in a cycle. I mean that's basically, it's like math, right? When you're in a race and you're doing track and field, if someone's running faster, eventually that fast person's going to catch up to you once it completes a cycle around you. Or maybe they're in the closer to the center of the track. But yeah, you had a question?
yeah, I was gonna ask, but now how do we know when node starts the cycle?
Where it starts? Where the cycle starts? You mean from here?
Yeah.
You mean like say it's this one?
Yeah.
Well, I mean, at this point it would be that node.
No, with the torus in here, like with all one space complexity.
Could we do it with that? I actually don't know. Can we?
Oh, yeah, we could.
We can.
You want to explain the code
What do you mean?
to explain it? Could it be done?
We can do it with tortoise and hare to find where it starts?
Yes.
Okay. I don't know. I don't know.
Do you want to take a photo of the code so I can teach it?
Yeah.
Because they asked me that in the interview.
Oh,
It's
for
very
real?
important.
Let me see. Let me see. Let me get the phone here. Let me see it.
It's actually pretty confusing. At least the second part.
Let me see it. Check this out. So according to Lazaro, this was asked in an interview. And this is something I didn't know myself. But apparently you can detect where the cycle begins using tortoise and hare and not using a hash set.
Can you just return like a tuple of care and true? And that would be the node that.
But that's the thing, we're trying to do it without a hash set.
So to have
Oh.
constant space.
We want to have constant space using what we did before. Yeah, this one's pretty interesting.
It is, right?
It is kind of interesting, yeah.
The second value.
Yeah.
Low-key breaks me.
Okay. So what we want to go over now is we want to return this value, and this is the value where the cycle starts, right? So that's basically what we're going to go over, and that's the code for this one. So we have the fast and the slow. And in damn it, this is Python notation. The fast is gonna, this is the first one, it's gonna equal to the first one. This is the second one, it's gonna be equal to the second one. You know, that's just like a inline. It's not the same as Java, where it's like a period, no, a comma. Where it's like int comma a equals b, comma c equals, no. Int a equals 1, comma b equals 2, comma c equals 3, semicolon. It's not the same as that, right? It's different. This the first variable is can equal to the first value here. Second variable is equal to the second here. I'm just differentiating the two. That's the difference between them. And then we keep track of whether there is a cycle. And at first it's false because we don't know. And then we do the tortoise and the hare, right?
Okay, let's see if they remember. Quiz them.
All right. I'm actually looking at, you don't need to check for slow. Because fast is always going to be ahead of slow.
Yeah, true.
So what else do we need to check for in the while loop?
Fast.next.
Yeah, so we need to check that fast.next is not null. Because we're going to make fast equal to fast.next. So we need to call upon the next attribute for fast.next. So fast.next needs to be a set object.
Equals if you slow.next.
What do you?
Change slow first, and then fast is equal to slow.next.
Okay.
So
Maybe.
you don't have to do fast.next. Slow is
Oh, okay.
slow is equal to slow.next, and then fast is equal to slow.next.
Fast is equal to slow.next. Why?
Because previously you did slow is equal to slow.next.
Right.
So that's moving one forward.
Yeah.
And then for fast, go back to slow and move one forward again. It's the same as moving two forwards.
Why are we moving fast back and then? So fast is going to be equal to just 1. So fast equals fast.next.
Wait, no, actually, yeah, you're right. We do have to change it by fast.
Yeah. We have to change slow and fast independently. Right? Which is the point. So,
Yeah,
oh
you're right,
my
that's
God. Yeah. Oh, actually, what is it? Slow equals what?
Slow.next.
So slow equals slow.next. So that moves it up by 1 node. And what about fast? What happens to fast? Fast equals what? I just said it.
Fast.next.
Yeah, exactly. That's this check. Here, we check that if slow is fast, right? What happens? What happens then if slow equals fast?
Return true.
Well, we don't want to return true. We want to return this node. Well, are we keeping track of whether there's a cycle or not? Yeah, we are, right? That's this one. So we say that if cycle equals true, and then we break. So we break out of this while loop. And I am running out of space. I'm continuing on, so after that we check. If not, actually, let me see. If not, is cycle. Then return. So if there is no cycle, return null or none. So that means that we ended up being at a null value. There is no cycle. But let's say there is a cycle. We did find one, right? So you guys remember that for this specific one, we ended up here, and that's where we stopped, right? So according to this, Yeah, the confusing part. So we have to move slow back. And fast stays there, right? So, nope, damn it. So then we check slow. It's not equal fast. So that's the only check we do, right? And we can do this. We don't have to check whether they're null or not because we just check that there's a cycle. So that means that we can do dot next and not worry about getting null. So we can keep getting the next attributes from these. So equals and fast equals fast dot next. So we start here, fast is here. So now fast is going to move at the same rate as slow. You move slow up. Get rid of this, that. And then fast moves up by 1. And then we move slow up again. And then fast moves up by 1. So now they're equal, right? So that breaks the loop. And then we return either, we could return either fast or slow, but this example says to return fast, right? So this is where the cycle begins. Okay?
What if there was a node before 1?
A node before 1?
Yeah.
That's the difficult part. Like, how do we know if we're just moving both of them one by one that they do meet up? What if they're always like
Oh
there's
my-
always a gap?
Oh my God!
But are they gonna meet up?
Huh?
How will they meet up if
Got stuck on my shoe.
Somehow they always meet up.
Got stuck on my shoe.
Like if there's a cycle, of course, because we've gone to that part. If you set slow to head, they would always meet up.
Yeah, they're always gonna meet up.
but now slow's at 0 and fast is at 5?
You know what?
But this might change where they met up.
Yeah, they might change. In fact, so if they met up here, and let's say now it's 3 instead of just 2 after this, so it might have met up here, right? Before we started this loop, they might have met up here, and that's this part. So I'm just trying to look at it, right? Why does this happen?
Right. It's
I think it depends on the cycle length. Actually, I am interested. I want to find out why. So depending on the size,
They do meet at 4.
they do meet up at 4, yeah. So what determines that it meets up here? Based off of this, right? The length of this. So it's based on the length of this and also the size of the cycle. So what determines where they meet up?
that's saying that we're in the beginning, right? Like where they're both equal to each other. Like here
Yeah.
in this case is 4.
Yeah.
The remaining nodes in the cycle is equal to the nodes they take
Yeah.
from head to
Yeah.
the beginning cycle.
Yeah, exactly. So,
But how can we confirm that math? That math.
oh, okay. So let's say we zero index, right? So the size of the cycle equals 4, and we say we zero index 1, 2, pre equals 3, pre-cycle size, I should say. Okay.
Yeah, cycle size minus 1 because fast stays on a node inside the cycle.
So you think,
So the remaining nodes is just cycle size minus 1.
so basically where they meet up is going to be cycle size minus pre-cycle size?
No, cycle size. Oh, where they meet up?
I mean, yeah, that's the point, right? That is probably where they meet up anyway, right? Because then that's the part that would make this work. If this is the solution to find where it begins.
Wait, cycle size minus pre-cycle size? That's what you said?
Yeah, cycle size minus pre-cycle size, and that's where they meet up.
Yeah, but before when we didn't have that 0 as the head.
Yeah, then it would have been 2. It would have been 4 minus 2. Then we would have ended up at 2.
Oh, at 2, yeah. Oh,
Yeah.
Wow, that actually works out.
Yeah.
But still, how can we confirm that?
It just works.
It just works.
It just works. I mean, I don't.
We need the proof.
We need the proof. I don't know how to. I don't know what the mathematical axioms are for this. So then, like, they would slow and fast meet up is equal to. Yeah, we're doing some complicated stuff, right? I didn't know it would come to this. Okay, yeah. All right, so that's where they meet up. Okay.
So 4 minus 3, they meet at 1?
Yeah, they meet up at this one. If we zero index from the beginning of the cycle,
Oh, the cycle.
they would meet up here, right? And then we zero index before the cycle begins, right? And the length is 3. So we just 4 minus 3 is 1. That is where they meet up. Because that's what's gonna make this part works. So yeah, Lazaro, that actually kind of makes sense. But like, but how do you know that before? How do you know that before this, right? How do you know that they're gonna meet up here before doing all this? Is that what you're asking?
No, I'm just saying like that second while loop, it's saying that they will always meet up. Like they will, because they're both being incremented only by 1,
Yeah.
and that's enough. But in my mind, like I kind of don't see that because what if like they're both always behind each other, and they never do catch up?
They do. They will.
They will.
That's the
yeah.
point of this.
No, okay, but can you prove it? Can you show me the math?
No.
Exactly.
I'm not a math
That's what
major.
I'm trying to get
Maybe
to,
we
like,
can ask.
I want to see
We
the
can
math
ask
for it.
Azar. He's a math major.
Okay, if you know,
Well, I
then
think
I'll-
apparently the point where they meet is equally distant to
Yes,
the beginning
yes.
of the cycle as
Yeah, the
as
length of
the
that.
head.
Yeah.
Yeah. So how many times did they go around? Right? How many times did slow? Well, how many times did fast go around the cycle to meet up with slow? That's an interesting problem.
Exactly.
Okay. I mean, how much time do we have? Oh wow, we only have 20 minutes.
Yeah, sure.
Wait, is it
22
50?
minutes. I was just counting.
Oh, okay. Do you guys want to go over this, or do you want me to? I mean, I should go over doubly.
Yeah, do double.
I'll do doubly. You guys figure out how many times fast goes around the loop to meet up with slow on your own time. Oh, and this, yeah, this problem is on LeetCode.
I think 1.5.
Hmm?
1.5.
For all cases?
But it makes sense because
For everything.
slow is gonna be at the half. So fast has to be 1.5. I guess.
Actually, that's a good point. Since fast is moving twice as fast, slow is going to move half the distance through the cycle as fast.
Yeah.
Yeah. Might have something to do with that.
Slow is gonna be at the half. So if fast
Oh,
catches
you know what?
up, it went 1.5 times.
Okay, so this is 1, but then like the end is 2. So it could be like the half of that. Oh no, it's 3. So it's like the half of 3.
That was just a wild guess.
You were just a wild guess. I wouldn't be surprised if it ended up working. Maybe. So really quick, I'm not gonna go into code now. I'm just gonna go into concepts. Cause I don't know. Have you ever found this doubly linked list problem on LeetCode?
No. There's probably some around.
Yeah, there's probably some, but I haven't encountered them. There is a problem that requires you to design one, but you know, I think I put it out. well, at least I picked it, and Lazaro pulls it up. Doubly linked list. So now we're going over doubly linked list. So now it's a linked list that doesn't just go in one direction. You can from any
Oh, this is a good one.
which one?
Flat and multi-level W link.
I was looking at that earlier, but I didn't know if I was gonna have enough time to go over it. And, and so. So it's like 1, 2. So we went over this. This is a singly linked list, right? It goes in one direction. You can while loop to go like this. But imagine, right? We had a node class we defined that was special and did not only have a pointer to the next node, but also had a pointer to the previous one as well. That's just what that is. Yeah, and that's it. Each node has a previous and a next node, and that points to a node object that is the same object. That it's a doubly, also has a previous, which is this, that. I mean that's pretty much it for that. Can you see if there's a cycle in here?
Yeah, the list twice.
Yeah, so you can go through the whole list like this. But you can also do this, and this. Right? So fun game. I guess this is gonna be our fun game. How many unique cycles are there in this doubly linked list? How many? Come on, big brain, big brain.
120.
120? Wait,
500.
yeah, actually might have been close. So here's an example of one. And I guess 2, 3, 4, 5. No. Yeah, literally just gave you the answer. Those are all the cycles there, right? So it's like
Is
a
this-
yeah.
Is this n times n minus 1 over 2?
N plus 1, n times n plus 1 divided 2. But it wouldn't be that.
Wait, why not? It works out in this case.
No. Because it's not. That's not the value. This is
N is the number of nodes. There's 5. 5 times 4 is 20 divided by 2 is 10.
5 times 4. It's not n times n plus 1. It would be n times n minus 1. So see, it's not.
That's what I said, n times n minus 1.
So it's
over
not.
2.
It's not sum to up to n, right? You know the mathematical.
Yes, that's what I'm talking
But it's the opposite. It's one
If you do
backwards.
plus 1? If you do
Yeah,
plus
they do
it
plus
does-
1.
Then it doesn't give you
It doesn't give you that. Yeah. So the
So the sum
But
of
mi-
n
minus
minus
1.
1.
so basically, how many unique cycles are there? And I just gave you the list of all of them. So it's 1 to 2, 1 to 2 to 3, 1 to 3 to 4, 1 to 4 to 5, right? And then I do 2. So I exclude 1 since I did all the ones for 1, which is this. I just do 2. So 2, 3, 4.
Dude, are you sure it's not that?
What? N times n minus 1 divided 2. I'm corroborating. I concur with what you said. Right? Like that's n. Okay, but do you guys see that those are the unique cycles? right? I do the 2s, then I do the 3s, and then I do 4, and then for 4 it's only 1. So how many are there? 10. So the number is 10. What's the math? So
This is the sum from 1 to n minus 1. 1 plus 2 plus 3.
Yeah. Do you agree with me?
I'm agreeing with you.
Oh, okay. I thought you were disagreeing.
Oh my God.
Oh.
So that equals to 5 times 4 divided 2, and 5
Yes, yes.
n equals 5. So it's equal to n times n minus 1 divided 2.
Yes. What
Yeah.
did you say plus 1? What are you talking about?
No, because I was talking how it's not this.
Yeah, no, I said minus 1.
Okay.
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 No, yeah. That's
Okay.
communication.
Okay. Miscommunication between me and Lazaro. And now he's dying of laughter for some reason. I don't know why.
I'm not dying.
Yeah, you are. Guys, is he dying?
I'm dying.
Yeah,
I'm
he's
serious.
dying.
I'm dying.
He's dying of laughter. See, everyone is agreeing.
Why do you have to pull out your gun and force us to agree?
I'm not pulling out anything.
Well, you're off the screen, so you could have been.
Oh. Guys. Okay? No gun. I'm not forcing anybody to do anything. They agree with me. Oh. Oh, wow. All right. Wait. No, it's not working this time?
No, I turned off.
Okay, it's turned off. All right. These are the unique cycles in here. I just did that for fun. I just did this for fun. But you guys get, so if I asked you to write the class for the node, what would it be? So class. I'll just call it node. Doesn't matter. What would it be?
Def init.
Yeah, def. Okay, and I made a mistake before, but so the first argument in the constructor is the self, right? Because the self calls it, the object calls it, and of course we want to keep track of what? We want to keep track of the value, right? The value. And let's say when we're creating the node object, but by default is 0. So we'll just say it's 0. Okay. Then we have next, right? The next one. So the next, by default, I'm going to make it equal to none. And now, what else did we add before?
Previous.
The previous one. So then the prev, by default, is going to be none. Right? So I have values here. If you don't insert an actual value, the constructor is just going to say that the value is 0 here. If you don't give it an x, it's going to say that the next is none. If you don't give it a prev, it's going to say the prev is none. So that's what this is saying. And so in here, I access the attributes. So sep.val equals val, much like this.val equals val, right? That's kind of what self is. It's a this. It's Python's version of this, as in this object of this class. Self.next equals next. So this is the attribute, and this next refers to this parameter here, this argument. And then prev equals to prev. All right? So I guess I could do this. So if I want to make a new node here, node 1. What would that give me?
5, none, none.
Right. So 5, none, none. So basically, it made the next one none and the prev none because I didn't put it in the constructor. So I would have, I guess I could just do this, right? it gives me node 5, a value 5. So I didn't put next and prev, it's none, none. Yeah. And then I could say node 2 equals node 3. And here, well, the ordering does matter, but you could also do this. You could also actually put the name of the parameter, the argument. And I'm going to put node 1. So what does that do? What does this one do?
It makes node 2 connect to node 1.
As the next, right? So,
But the previous of 5 is disconnected.
yeah. So the next is this one. Oh. It's a pointer here. And then the previous is none. 2. Okay? All right, yeah.
Wait, the previous of 5 2 now.
Right. So I did not say that the previous of 5 is this. That's a good point. Right. I didn't. Thanks for catching me on that. And say I want to change it. I could just say this. Right. I do this, and that already sets it up such that now the previous is node 2, which is what we called here. Okay. So let me see. Any questions about this? It's all pretty clear, right? All right. What do you think? You think we should just?
Please. My battery's about to die.
Your battery's about to die? Okay. Well, why not just? Oh.
But then I'll have to move everything, and it looks really good when it's up close. Like
Yeah.
Quality.
It does look good, but then they're gonna. All right. Whatever. Gonna close look of my face. Okay. So I'm gonna leave it like this. You know, pretty simple stuff today. Next class, we're gonna go over trees. Particularly, I think it's binary search tree to start off with. Yeah. So we're gonna go over that. Tree traversal, also, I'm gonna do that as well. So be sure to look out for that. Keep doing the leak code questions. I'm gonna add some new ones. We're gonna keep drilling you guys over all this stuff. This Friday we also have the binary search night, and also don't forget to sign in with the QR code that's in, I believe it's in this direction. QR code is in this direction. So yeah, do be sure to sign in with that if you're watching through the stream. All right? And so yeah, that concludes that, and be sure to come to our binary search night. All right.